Okay, let's just jump right into this explainer. What if literally everything we thought we knew about the universe was just wrong? Today we are exploring what I think is the absolute greatest cosmic whodunit of our time. And to truly appreciate the sheer scale of this mystery, we have to map the cosmos on a scale that honestly pushes the very boundaries of human engineering and fundamental physics.
47 million. Seriously, let that number sink in for a second. That is the staggering number of galaxies and quasars the DESI project successfully mapped over its initial 5-year mission. And get this, they actually finished it ahead of schedule. They gathered data on 6 times as many galaxies and quasars as all previous measurements combined. They basically created the largest, most detailed, high-resolution 3D map of the universe ever produced. It is mind-blowing.
So, to actually gather this absolute mountain of data, the Dark Energy Spectroscopic Instrument, or DESI for short, uses 5,000 individual robotic fiber optic eyes. It's kind of like a giant, super precise insect eye. These positioners swivel around and lock onto distant pinpricks of light with an accuracy of 10 microns. For perspective, that is less than a tenth of the width of a single human hair. This incredibly precise choreography allows researchers to trace cosmic history back 11 billion years, streaming 80 gigabytes of raw data down to their supercomputers every single night.
Now, before we get too deep into our cosmic investigation, it's crucial to just clearly define our two main cosmic players, so we don't mix them up. First, we have dark energy. This is that fundamental ingredient making up about 70% of our universe, and it's the mysterious force driving the universe's accelerating expansion. On the flip side, we have dark matter. This is the invisible form of matter that accounts for most of the actual mass in the universe, pulling things together through gravity. Understanding how these two interact, well, that literally dictates the ultimate fate of everything we know: our galaxy, our solar system, the very atoms in our bodies.
Section 1. A cosmic mystery emerges.
So, the mystery officially kicks off when researchers started crunching the first 3 years of the DESI dataset. Now, they were fully expecting dark energy to behave as a steady, unchanging constant. Standard model stuff, right? But instead, when they analyzed how galaxies clustered in the past versus their distribution today, the data fingerprint from their observations revealed a very distinct dip and rise. That specific shape strongly hints that dark energy is actually evolving and changing its strength over time. It's a massive anomaly. I mean, it literally sent shockwaves through the entire astrophysics community.
Section 2. The problem with phantom energy.
This brings us to the prime suspect for this anomaly: evolving dark energy, acting as a sort of phantom energy in the early universe. But here's the catch. This creates a massive, almost insurmountable problem for our current understanding of physics. You see, to make the math work for this evolving dark energy, a cosmic metric known as the equation of state has to drop below -1 in the early universe. And in fundamental physics, crossing that threshold violates what is called the null energy condition. It implies catastrophic cosmic instability. It creates theoretical models that just become entirely pathological. So it essentially breaks the fundamental rules of the universe as we know them. Not exactly ideal.
This theoretical nightmare leads us to step back and ask a totally different question. What if we've got the wrong suspect entirely? Is there an explanation for this exact same data fingerprint that doesn't require us to completely break the fundamental laws of physics?
Section 3. A new suspect: exotic matter.
Enter astrophysicists Xingong Chen and Abraham Loeb. They published a fascinating paper outlining a genuinely brilliant alternative, introducing a tiny component of exotic dark matter into the mix. Unlike evolving dark energy, which, remember, violates that null energy condition and implies dangerous instability, this tiny fraction of exotic dark matter has an equation of state that just oscillates up and down. Because it never drops below -1, it completely obeys the laws of physics and maintains absolute cosmic stability. It's a much safer suspect.
Section 4. Matching the fingerprints.
But, a theory is only as good as the evidence it can actually explain. We really need to see if this new, safer suspect can produce the exact same anomaly we saw in the DESI data. Well, if we compare the mathematical fingerprints of these two theories side by side, the resemblance is completely uncanny. On the one hand, we have the anomaly hinting at evolving dark energy, the rule breaker. On the other hand is the fingerprint produced by Shen and Loeb's exotic dark matter model. You can plainly see how the exotic dark matter perfectly mimics the dip and rise of the anomaly. The shapes match beautifully. It's almost like a cosmic disguise.
So how exactly does it do this? Well, this alternative theory breaks down into 3 pretty elegant steps. Step 1, dark energy gets to remain a standard, boring cosmological constant, exactly as Einstein originally thought. Step 2, we introduce that very small fraction of exotic dark matter that undergoes a rapid oscillating equation of state. And step 3, because we traditionally just assume all dark matter is standard cold dark matter, this tiny oscillating fraction effectively tricks our observations. It creates a mathematical illusion that perfectly mimics an evolving dark energy.
Section 5. The future of cosmology.
Okay, so we've got two competing theories firmly on the table here. One is suggesting the rules of physics are broken, and the other is suggesting a strange new dark matter trick. Fortunately, the jury won't be out forever. Because of its incredible success and sheer efficiency, the DESI mission is actually pushing well beyond its original 5-year plan, and it's going to operate right through 2028. Their goal is to expand the sky map by another 20%, pushing through the really challenging plane of our Milky Way and even deeper into the cosmos, just to gather the final, decisive data we need to solve this.
Which brings us to the ultimate question we are left with today. Will our universe's expansion force us to rewrite the fundamental laws of physics, or are we simply going to uncover a strange new oscillating particle that's been tricking our telescopes this whole time? Only more data is going to tell us the ultimate fate of our universe, but whichever suspect is finally found guilty, our understanding of reality itself, it will never be the same.